the O reduce. So let's go. What we observe is that when we use comparator graph to trace the backward, because we register the post-gradient hook and doing the O reduce inside post-gradient hook. So what we imagine is that this O reduce should have some relation with the accumulate gradient operation, because after accumulate gradient operation, we can then do the O reduce to reduce the gradient. And in fact, when we get the graph, we see that the backward graph has two kind of input. The first input is the parameter itself. The second type of input is the gradient. And the accumulator gradient operator use the parameter, but internally it will also modify the gradient. But from the graph, you cannot see it actually depend on the gradient. On the other hand, any operation in the post-gradient hook actually use the input, the gradient input. So we don't see any relation between the node, the accumulated gradient node, and the node of the operator in post-gradient hook. So when we do the reordering, it is possible that we actually reorder the O reduce before the accumulator gradient operation, which will result in incorrect accuracy. That's the main issue we currently observe.
Thanks for the introduction. So, if I recall correctly, Brian, you had a proposal for what we should be doing in this case. So, do you want to tell us the proposal?
Yes. Here, I'll share my screen
Yeah, sounds good.
for the example. Oh, sorry. Okay. So this was the repro code, and the repro code is basically running compiled autograd, calling backward, and ensuring and okay, it's calling backward, and there is a post accumulate grad hook involved, which is this hook. And if we look at what the graph of the backward looks like from compiled autograd running, there's like a couple interesting things going on. So one is that there's this accumulate grad node in the graph, which is expected today because there's like a primitive op for that. Um, and the other interesting thing is that if you look at the graph inputs, there are how many? There's L input 0, 1, 2, and then there's this fourth argument, which is L inputs 2 grad. And that is already a bit strange because if you look at like what's happening in this example, at the time that we call backward, which is what should like run compiled autograd
Actually,
and run the
Brian, I have a
compiled
quick question.
autograd.
Is this graph post AOT autograd or produced directly by compiled autograd prior to being fed to Dynamo?
This is produced by comparator, and it's going to be fitted to Dynamo.
Okay. Sorry. Okay, go ahead.
Oh, sorry. Fitted to inductor.
Sorry, yeah.
This is post AOT, yeah.
I think this is pre AOT autograd, but post Dynamo. But someone can correct me if that's wrong.
If you look into like the compiler function, I actually put out this before I fit into inductor.
Like if you this print comes from the def inner in the code repro above. So it's right before we call inductor.compile.
Yep, it's before we call inductor.
Oh, okay.
So this should be just after compiled autograd, I think.
So
I guess
maybe we didn't exactly run AOT autograd, but this is morally after we've lowered everything to a bunch of plain A10 operations right before we send it to inductor.
I think that's fair. I guess it depends what compiler you pass into compiled autograd. And in this case, like we end up rerunning Dynamo and AOT autograd on whatever this backward graph is.
Yeah, but the print is of GM underscore. I just want to be clear about what graph we're talking about, because some graphs may be valid earlier in the pipeline and invalid later. So it's important to know where we are. So this is right before inductor. So that is clear to me. So you can keep going.
Okay. Right. So back to the like input situation. So one thing that's like a little bit strange is that there's this L inputs to grad input, which looks very much like, oh, we're passing in like the dot grad field of input two as like one of the inputs to the graph. And the reason that's like a little weird is because before invoking the back, like as part of invoking the backward, before we've invoked it, the dot grad field of one of these inputs should all be none. And it's like the act of running the backward and running this accumulate grad logic that sets the grad field. So that's like one weird thing about the graph. There's like two other weird things. One is what Animesh pointed out in a related issue here about how we're like recompiling a bunch. And I think that's because Animesh pointed out we're guarding on the fact that this grad field exists, and then we keep failing that guard because at like when we're about to try to run a bunch of guards and run this graph, we see that like L2.grad doesn't actually exist. So those two things seem related because we're both like lifting an argument to a graph input and guarding on it, even though we know that .grad doesn't exist. And then the third weird thing about this graph is basically the ordering problem, like mentioned in this original repro, which is technically there's an order of ops that we expect to run here, which is that accumulate grad should run first, and then the contents of the post accumulate grad hook should run second, where like the stuff I've highlighted is basically what's inside of this hook. And according to like the dependencies in these nodes, there's no guarantee that that'll happen. And that's because here, like this hook takes in a param and then does stuff like param.grad divided by 2. And the way that's represented in the graph is that we grabbed this input from the graph directly, inputs to grad divided by 2. And now there's like no notion of a dependency that this thing cannot be used until after the accumulate grad runs. So I guess that's like in my head what the main three problems are with the graph. Any questions before I talk about like one proposal?
Yeah, go NYC.
So my read here is that call hook, the argument on the line you're highlighting, call hook is the param on which you're going to access the .grad field or what the original code is accessing. Do we have other systems where we have a similar thing where a tensor or an object abstractly contains another one, and we basically hide things from ourselves this way?
I'm going to hijack your question, Alvin, and I want to talk about invariance. So historically, with the general model we have is when we call inductor, we're giving inductor a plain old graph of tensors, and then inductor produces some more tensors. And there's just plain tensor compute on these tensors. This is nice and simple, and AOT autograd was supposed to have gotten rid of anything complicated like autograd or anything like that. So under this model, it is not okay to access the .grad field inside an operator, inside inductor. Now, I understand that there are some like countervailing considerations, which is why accumulate grad being an actual node is like convenient when we do compile autograd. But there's definitely something very strange going on here. Albin, does that answer your question?
Yes. Yeah. That's exactly my question.
I don't know if we have Jansel here, actually. He would be very helpful.
Yeah, I mean, I think like arguably like accumulate grad is not a functional op, or I guess it's definitely not a functional op because it's mutating the .grad field, and so you know, we like one thing we could do is we could say you know, we're going to functionalize accumulate grad, and we're going to basically like model behavior, the effect that accumulate grad is going to have on the .grad field. And you know, rewrite the graph such that all the grad manipulation happens sort of outside the graph in the functionalization preamble or suffix. I think in sort of in practice, once things get to inductor, we're already dealing with non-functional operations in lots of different places. And for performance reasons, like you sort of have to, because there's some cases where functionalization sort of causes sort of catastrophic performance impacts. And so, there's ways we could handle that. Like basically, like currently in inductor, any op which ends in an underscore, we'll assume it's a mutation op, and we already will like not reorder things across it. But I think sort of like a more complete proposal of like how does functionalization handle accumulate grad underscore is definitely worth considering.
Also chiming in, the like accumulate grad also having like three potential ops that it's like three different behaviors that it's desugaring to, where there's like either like I think you depending on pointer ref counts and depending on like whether the grad exists, like we'll either assign or we'll do like an out of place add or we'll do an in place add. Like having those three different potential behaviors doesn't like compose with CUDA graphs, because like of course when you CUDA graph capture, you're going to freeze in one of those behaviors. So at least for CUDA graphs, like we would need to either figure a way to guard such that we have like consistent behavior, rewrite it in a way that that a consistent behavior occurs, or like do the epilogue like in AOT autograd. Unless anyone has any other thoughts.
Yeah, and that's why the current system is guarding on the existing value of the grad, because if you don't guard on the existing value of the grad, it'll be incorrect.
NYC.
I guess to continue on what Elias was saying, to what extent do we want to say that by the time we reach inductor level, we should have multiple accumulated grad overloads? One, and because we already guard on what is the state of the grad field, so we should have one that takes only the gradients if it does nothing else, and the side effect is handled somewhere else, or that takes the gradients and the existing .grad field if such a field exists, or whatever is the right low-level functional op we need. Would that be the right way to put back that grad attribute into the graph?
Yeah, I think we should definitely have resolved which overload of accumulate grad what we need by the time it gets to inductor, because we're already guarding on all the stuff that should make it deterministic.
Okay, any other questions?
But although like one other thing I mentioned for that is that we should we might, if we're going to do that, it might make sense just to decompose accumulate grad into one of those three overloads rather than keep it as an op.
Okay, Brian, I don't know if you want to still present your proposal or you want to modify it based on the discussion we just had. Both would be okay by me.
Yeah, we can modify it. Because I think that part is kind of independent from from my proposal.
Okay, tell us your proposal.
Sure. So one question is, what do we do about accumulate grad, aka the stuff we're talking about? And then there's also I guess they're all related. I basically tried to propose what is the graph that we want, and maybe the accumulate grad bit we should change based on this discussion. But here's a proposed graph. And what's different about this graph? So one difference is that there's no extra grad input to the graph, which reflects the fact that the grad field is none at the time that you're first checking guards and executing the graph. The second is that there is now this dependency relationship between the stuff in the hook that use the parameters grad and the result of running accumulate grad. And the way that that's set up in this particular graph is that this graph requires accumulate grad to return the updated grad field as its output, which is pseudo functional, like here, accumulate grad is still technically mutating because it's like accumulating into the .grad fields of the parameter, but it's also returning it's returning the updated grad as an extra output. And then somehow we need to make sure that like any downstream code that uses the .grad field in the parameter knows to grab like this value instead of directly reaching in and calling like input to .grad directly in the graph. So that was one proposal. I guess maybe one way to augment it based on what we're saying is we don't want to see this directly. We want to see we either want to decompose this directly so there's no accumulate grad at all in the graph, in which case the like actual grad accumulation is some side effect that needs to happen somewhere else. Or we keep that accumulation in the graph and instead we desugar this into some like more specific overloads of accumulate grad that represent the like different branching that it does today based on what we have to guard on.
Brian, can I yoink the screen share?
Yeah, go ahead.
Great, thank you. Okay, so I want to explore the proposal that Elias and Jansel had, which is desugaring the overload a little more. So concretely, if we desugar the overload, it seemed like there were a few cases that we needed to handle, right? So there is pre-existing grad entry, ref count equals 1, pre-existing grad entry, ref count greater than 1, no grad entry. Okay, so let's do the easy case first. So when there is no grad entry, I think everyone agrees.
There's a correction there. So the ref counts that it's actually checking is not the existing grad field. The existing grad field can have as many references as it needs. The ref counts that it's checking is the new grad you're adding, and it's only that only matters if there's no grad entry. So if there's a pre-existing grad entry, it's yeah, so there's if there's a pre-existing grad entry, there's actually two cases. There's one case where like the layout and there's a bunch of like layout checks that deal with like sparsity and stuff. That are pretty annoying and very subtle and hard to but the common case is it just becomes grad plus equals new grad.
And in the uncommon case, it's
in the uncommon case, it's going to reallocate the grad tensor because the existing grad tensor did not have the satisfactory layout / sparsity.
Okay. All right. So,
and I think it's actually not equals 1. I think it's actually equals like 2 or something because there's some reason why there's 2.
Well, basically, this is the one we're stealing as possible.
Yeah.
Yeah.
Oh, okay. So fine. So I think the easy case is the common pre-existing grad entry, grad plus equals new grad. So let's talk about what graph I want to see in this situation. So Brian, in your proposal, you propose that we eliminate the grad input from the argument to the overall graph. Is that right?
Only in the case where there wasn't, well, sorry, I guess in the repro that we were looking at, the grad was none before.
Okay, so maybe okay, so all right, so let me give a proposal here. So I propose that in this situation, I do want to see a grad input into the graph. And then I want to see the desugared code should be something like L X grad add underscore new grad, where new grad is an intermediate.
Shouldn't that get functionalized before inductor?
Well, I don't know if it should be functionalized or not. So if it's functionalized, okay, so non-functional is this. Functional is lx grad new equals lx grad a10 add lx grad new grad and then return lx grad new at the end.
Although when that gets mapped to inductor, it'll actually become a copy underscore at the end of the graph, so that we can fuse the copy into other things.
I guess this is fine. So as far as memory lifetime is concerned, we're not keeping the main problem is we keep the old grad live longer than necessary. Is that right?
So if you return it, then you basically, if you return it outside the graph, then you basically double your memory usage, because you need like the original grad memory plus the copy until the graph finishes. While if it becomes a copy underscore in the graph, then inductor can potentially run the copy underscore earlier and release the memory earlier in the graph. So like there's basically like the functional version has strictly worse memory behavior than the non-functional version.
Okay, so let me just modify that. So non-functional-ish is you do lx grad new equals, you can add lx grad new grad, and then later you do lx grad copy underscore lx grad new. So if we were to generate this, which is what we currently do for when we fuse in copies into the graph, Jason, you're just saying we'll get reasonably efficient code in this case?
Yeah, basically in this case, it's up to inductor to inductor actually probably doesn't do an optimal job of this today, because it doesn't do memory aware ordering of operations. But at least in theory, if we did teach inductor to optimize for memory usage, it would realize that, oh, if it moved the copy up earlier in the graph, it could delete lx grad new and have a lower memory program.
NYC.
Just to mention that these in place are usually non-differentiable. So I think it's very possible that we will be able, like AOT autograd doesn't have to run these outside of the graph it compiles. So in the usual case.
Well, we're talking about compiled autograd anyway, so it's not.
There's no grad.
there's no grad anyway. Okay.
Well, no, you can have like, if you said create graphs equal true, you will have gradients in there. I'm just saying it's non-common, so it's fine to ignore, but I would still leave that asterisk.
Okay. Alvin, what about create graph? Okay, I'm not sure which one we should do next. Should we do
one correction? The line above that, the main downside keeps LX right there.
Yeah.
It's keeping LX grad new live longer than needed.
Oh yeah.
Okay. LX grad never gets freed at all. By design.
Okay, so I want to skip the cancer case and go straight to the non-stealing case, because the stealing case is kind of weird, so I think that one's more complicated. So, okay, so Brian argued we should not see a grad input into the graph, which I agree seems very reasonable.
Well, the grad input is none, so you it would be impossible.
It would be impossible. So I mean, it's very buggy right now. What we've got, Brian. So what exactly were the operators you were expecting to see here?
I think other than that, pretty much the same as what you put above. Like, there's no grad arguments to the graph.
There's no old grad, so we're just like. We just return the LX grad that's computed in the graph, right? That's it.
I would say yes.
So accumulate grad would be sugar into just like return the new grad.
So my hot take is we should make it impossible to ever hit this case.
Okay, well, then let's move on. I'm not sure how we're going to make it impossible, but let's talk the stealing case.
But the thing is that like when inductor is returning tensors, if inductor is returning a tensor created by inductor, we should be able to prove with 100% certainty that there's no stale reference to that tensor. Like, so if inductor allocated and created a tensor, then the reference count is logically 1, although in practice maybe it's 2. And like, where did that extra reference come from? Like, how did that extra copy of the grad appear? Well, that extra copy of the grad can only appear outside of the inductor graph, because inductor is not keeping pointers to the tensors it created after the graph ran. So it should be impossible for someone to get a reference to an inductor generated tensor before the inductor graph finishes. And like, if it's the case that like the tensor is getting used in 2 places after the graph, we should just generate a graph that returns 2 tensors, and the tensor and one of the tensors should be sort of slated to become the grad tensor, and then the other tensor should be slated to become the alias that is going to get created later.
NYC.
I would mention, I think this case potentially can happen if you have a graph that basically populates the same gradient into 2 grad fields. But I agree with Jason that we most likely know everything we need to know in inductor here. So
yeah, I think in that case, like, we should insert a clone into the graph, and the graph should just return 2 copies of the same tensor. And probably the kernel that generates the tensor would just write 2 copies of that.
Simon?
Yeah, doesn't this also happen when we have post hooks, where the hook it takes in the grad as an argument, and this is all before the inductor finishes
we're
running?
inlining all the post hooks. So like with compiled autograd, the post hooks just become they just go away. They just become part of the graph.
Okay.
Okay, I actually did something very naughty here. I said that we should just return LX grad, but to get a graph that's identical to the one before, actually I should be like setting the dot grad on a tensor in the graph. Are there any opinions about which of these people prefer to do? So it's basically a special op called set grad, which sets the grad field on a tensor.
So my read was that from what you were saying, at the inductor level, we want real functional ops. Any of that mutates the dot grad, the actual dot grad field on the tensor would not fit that definition.
I definitely have a bias here. I'm just checking if there isn't a good reason to not, do the functional version. Okay, so let's just commit to this thing for now. Okay, so then but there needs to be some code that actually knows to like shove these into the dot grad field, and I'm not sure. Is that Dynamo? Maybe that's Dynamo.
I think that's functionalization, because I think Dynamo like, because basically what you're doing is you're basically taking a mutation and you're moving it outside the graph. But like, Dynamo is usually capturing the program as written, including sort of the non-functional parts of it. And there's certain and to actually know whether you're in this case or the previous case, I think you need some function. It needs to happen after functionalization, I believe.
Would a good mental model here be the same way when we handle custom subclass and you set an attribute on that custom subclass, who is responsible for that attribute being set when you compile the subclass?
I think right now the set adder would be lifted as part of Dynamo, but I'm not sure. We might just graph break on that today. I'm not sure.
Okay.
Doesn't it matter who's doing, like, there's an accumulate grad, and then someone is tracing inside of it, and there's some branch that says like, oh, in this case we need to like modify the dot grad field, but in that case we don't. And isn't it like whatever some subsystem is in charge of like seeing that branch, which maybe Dynamo is the one that does it, or maybe make effects tracing or whatever is the one that sees it. I guess only once you like peek inside the accumulate grad do you know whether or not that mutation is needed.
Well, in this case, like we're in the no grad entry case, and in the no grad entry case, it happens. This happens 100% of the time.
Oh, sure. Yeah, you're saying like given other state, like the current state of the grad of the dot grad field, you kind of like know in advance what accumulate grad will do.
Yeah, if it's none, then it's either gonna set it or it's gonna clone and set it. There.
So I think another way to answer this question is when AOT autograd gets a graph, does the graph given to it by Dynamo, is it allowed to have dot grad like x-axes and stuff?
So currently, I believe it's lifting the dot grad axes to inputs to the graph.
Yeah, so that actually suggests that the setting the dot grad fields should be a Dynamo side thing.
Yeah, I mean the problem is that Dynamo doesn't actually have enough information at Dynamo time to know whether it should be set because of the second case in the overload. And also because of hooks can have side effects.
Well, but Dynamo is actually going to trace into the hook, right? That's the whole point of compile autograd.
Yeah.
Okay, I want to give time for Horace to present his thing. So let's work this out in some more detail offline. But I think this desugaring idea seems pretty promising. And I think it is good that we decided that we're not going to have a dot grad setter in the inductor graph. I'm happy because this makes the inductor IR simpler. And assuming it all works out, well, there's some details on Dynamo, but I guess we can figure them out. Who is working on this? Chin, are you going to like try to implement this or what?
I was planning to look at Dynamo changes.
So Animesh, you're going to look at the Dynamo changes.
Yeah.
Okay. Animesh, do you like this plan? Does this make sense?
It's still unclear about a few things, but yeah, we can discuss offline. Like how.
Why don't you tell us what you're unclear about?
I mean, the no grad entry, new grad ref count. I think, like, where should we do this? Should we do this in Dynamo? Should we do this in AutoGrad? I think that's what I'm unclear about.
Okay. All right. Thanks. Horace? Oh, do we have Horace?
Yes.
Okay. Go for it.
Okay.
I want to stop sharing my screen. Give me a sec.
Let me share my screen. So the rough picture is basically activating checkpointing is a very important feature. It's essentially a required feature for large scale training. Like everybody uses activation checkpointing. Like ads. Actually, they're many like internal teams use it. Like GenAI Llama uses it. Lots of external people use it for large scale training. And essentially, overall, my opinion is that like currently we don't provide enough solutions that solve the problems people are looking to solve. And this number two, the solutions we provide are not hardened enough, particularly in combination with Torch compile. And also, kind of partially related to the we're not providing enough solutions for folks. There's a significant number of internal teams that have like built various kinds of automated checkpointing solutions at various levels of sophistication and robustness. Off the top of my head, I know Ads has built one. I know Xformers has built one. I know Genie has built one. I forgot whether MRS has built one or not. And so overall, the two main things I think we need to build are or such work on are I'd categorize basically into hardening and automation. Number one is like I think there should be like more hardening and compositionality between like activation, checkpointing, and torch compile. And so in particular, this is kind of driven by a couple of examples. So one of them is that like for the FP8 stuff, I know Driss and I think Brian have had a lot of struggles on various kinds of memory saving issues. Part of it is related to like the min cut activation checkpointing itself. I think has some um, bad interactions in some cases. I think particularly with autograd.function. But the other thing is that I think they're having cases where like the overall torch compile is not like respecting their annotations. And so essentially, I think we need to like investigate these. And essentially, I think the North Star for me is that when torch compile is applied on top of activation checkpointing, it should basically never have a higher peak memory. Probably, ideally, it should be like strictly better in terms of peak memory as well as runtime. And so there are like I think many cases today where this isn't the case, just from like testing various things, and I think also like borne out by previous experiments from like Animesh and folks. And essentially, I think we need to like drive this down. Essentially, I think yeah, there's a number of particular concrete use cases I've seen, but I'm sure there's more that we need to look at. Okay, so I think the first part is maybe not so controversial. The second part I think is the part I think needs more discussion. And I think it also relates to a little bit about like our philosophy on what we want to support in a Torch compile future. So the general thing about automation and the way I've kind of been thinking about it is that the general difficulty is that one, we kind of want to balance a couple different things. So one is it requires the least effort from the user to like get their desired outcome. Two, we want it to be like predictable slash robust slash like overridable by the user in some way. And number three, it's easily composable with existing systems. And so, unfortunately, one, I think obviously clashes with a two and three to some extent. And so because of that, I think there's kind of three levels of reasonable automation I think we can provide. And so I've categorized them as like levels 1, 2, and 3. So level 1 is basically just a nice API for selective checkpointing. And this one I think is important. So this one should work in eager and compile identically. And so basically the main issue here is so for folks who are unaware of selective checkpointing, it's basically so activation checkpointing is typically the idea is that instead of saving all your activations, you only save like the beginning of the function, and then you recompute the entire function in the backwards pass. Selective checkpointing is saying, okay, I don't recompute the entire thing, I save a number of values, and then I recompute everything else in the backwards pass. And so we don't provide this API today, at least there's kind of an API. I think it's not like very robust and it doesn't work in eager mode. And so I think this is kind of straightforward. I think it's like a table stakes feature. I think we just need to provide a way to do selective activation checkpointing. There is some, I think, a design discussion about like how exactly this looks like. Like, do we provide like a fixed set of policies? Do we provide like some kind of open-ended Lambda function that people modify, or like some other kind of specifier? So in particular, part of the issue here is that we want to be able to do things like you have 3 linear layers, you want to be able to specify, I want to recompute 1 and 3, but not 2. And so it's not necessarily that clear how this API should be specified. Number 2 is basically this is kind of mostly in line with the Xformers activation checkpointing work, if folks are familiar with that. The main idea here is that we want an API that allows us to automate what to save in order to hit like a given activation memory budget for that region. And so like the way this looks like in Francisco's note, he also posted this publicly somewhere, but I just have this one open. It's basically that like you have this like, activation memory from like, 35 gigabytes down, or like per layer is like, some smaller amount, but from the 35 gigabytes down to like 8 gigabytes. And so this represents the activation memory that is being saved per layer. And so you just provide like a number from 0 to 1, where 1.0 represents saving everything, 0 represents saving nothing. And given that number, it chooses, like, it figures out a policy that like tries to maximize throughput while hitting that memory budget. And so the end result you see like a kind of like this Pareto frontier type thing from choosing different values from 0 to 1. So I think it's maybe not as obvious why we want this level. And so I want to contrast it to kind of like level 3, which is maybe like the most automatic version of this API, or like, of activation checkpointing, which is basically something like the user does not even specify that a region is checkpointed, right? The entire point of like checkpointing is to stay under like an and so basically we just make every single decision needed in order to stay under a max memory threshold. And so I think there are many users who want something like this. But the problem is that I think there are a lot of things that people do that make this extremely difficult to actually provide as an API. So one example is like, like oftentimes today when people apply FSCP, they graph break per layer. And so that, kind of instantly makes it a lot harder to, or like that instantly makes it a lot harder to apply an API like this, while like level 2 API that is specifying the checkpointing at the granularity of each module still, works perfectly well. I think another really good example to me is, let me see. Somebody messaged this one yesterday. So it's basically like for pipeline parallelism, there's some like differing amounts of memory usage per layer. And this is dependent on things like what is your pipeline parallelism structure, how many microbatches are you sending through. And so they end up choosing a different level of selective checkpointing depending on whether you're like the layer 1 or like layer 5, and depending on how many microbatches you're passing through your model. And so maybe you can imagine a future where we capture like everything in the graph and we do all the global planning all at once. But I think that future is like a little bit hard to manage, and it's quite a bit far off from where we are today. And so I think a level 2 API, I think makes a lot of sense from the perspective of it's like fairly predictable and also provides quite a bit of automation that folks want. I guess I saw there were a bunch of comments on the doc, but any immediate questions that folks want to bring up? I also want to comment a little bit about the graph break stuff if folks don't have any immediate questions.
Tell us about graph breaks.
Yeah, so part of the, I think, discussion on this API, and I guess maybe, so yeah, part of the discussion on this API kind of relates to, so for like a level 2 API, I think we basically, it's very, so the initial discussion happened basically that we want to, like there was discussion about like today, Torch compile does not work over activation checkpointing if there's a graph break within the activation checkpointing region. And so it is possible to make this work, maybe, but I pushed back on this because it wouldn't work for things like selective checkpointing. And also like, wouldn't really work for, kind of like level 2 APIs that allow you to like, more automation. And so my general push here is that I don't expect graph breaks within an activation checkpointing region to be like a big deal. And so I'm kind of curious about folks' views on this. So the general way that I kind of view graph breaks is that there are a bunch of different categories of graph breaks. And the rough way I would split those down into are like incidental. So like people like print stuff, they like, log stuff, whatever. And these are, or like there's some Python feature we don't support. And these are just kind of like stupid. So that's like up to the way that people are writing code. And so I don't expect those to exist within or like basically I am fine to provide features that require like those category to like not exist. And in practice, what that means is that if like I generally do not consider like graph breaks at the innermost level, like deep within a module to be like something we really worry about. So I guess I'm curious about what folks think about that statement.
I think that's easy to say in theory, but not true in practice. Like the delimitation from like a print statement causing a graph break to everything else is like not always so clear.
What is everything else? Like
I mean, like I think me having in the FP8 workstream, like a lot of the work is removing graph breaks. Some of them it's not as like a 10-minute workflow. It takes some time and some understanding.
So sorry, there's category one. The second category of graph breaks I would consider is stuff like things we do not like, or like it's more like conceptual things that we do not support, such as the like previously autograd functions are things that we would graph break on. And so I think it's very much worth resolving like category two. But I am a little bit more skeptical that it's worth our time to worry that much about category one graph breaks. And so in particular, the question, like the decision here that we're trying to make is it worth investing more in activation checkpointing APIs that require no graph breaks in the middle of the region? Or is it that we care a lot about supporting graph breaks in the middle of the region? And so if we are moving more functionality towards not graph breaking, or like if we're moving more functionality towards a world where we assume no graph breaks in that region, like is that problematic or not?
I think if that's the case, I think every type 1 needs to be like have the most perfect error messages telling you how to fix them, which I don't think is the case today.
Okay.
We have a sense of like how many type 2 like graph breaks. I think you mentioned like dynamic data dependent control flow is like one of them. I'm just curious if there's like, I don't know, like a list of these where we expect to support these in the future. And so like, we have a plan for actually fixing all of these versus like, or maybe that's not like really a goal. And then as long as we support like a good amount of them that most people use, like it's okay to not support graph breaks because of that, like because we plan to support like the high priority ones.
I'm not sure if there's an explicit list, but it's basically anything that you would say like Torch compile is not composable with today. So I guess off the top of my head, like things that we have more restrictions on are things like data dependent control flow, autograd function, tensor subclasses, things like this.
You might want to talk to specific customers to just like try to come up with a list of people we want to satisfy with this feature.
I'm pretty confident that the customers we talk to want level 2.
No, I meant about graph breaks. Like, I mean, I think Tesla, for instance, had examples of all kinds of weird stuff in their models that prevent it from working with graph breaks or AC in the past. And so do we care? Like, should we prioritize that or not?
Okay.
And how many other customers are like that?
Yeah, I feel like it's worth considering like supporting graphics as an option if it's like we have a sort of a long tail of features that that might be hard to support, and that'll take maybe years to support or something.
Right.
Then
So
it might be
I
worth
guess my question here is I think there are a lot of cases where we have features that have pretty questionable interactions with graph breaks today. I guess at least when I was like previously following FSDP, it wasn't clear to me like how we would support arbitrary graph breaks within like an FSDP region. Has that changed?
I'm not sure why that wouldn't work today with the graph break FSDP approach. Are you talking about compiled FSDP or graph break FSDP?
Compiled FSDP.
Okay.
I actually don't remember. I feel like compiled autograd changed a lot of the equation here.
I don't think it does because like the predominant thing that I think is very weird to solve is like you need to prefetch the next layers all gather before you like start this layer. And I'm not sure how we support that with something like graph breaks in the middle.
Well, this is the old discussion we had, which is that like if eager mode knows like how it's bucketizing and when to do the fetches, then compiled FSDP can't improve on this decision, but it can always like do what eager would have done, even if there are graph breaks. And then if you are able to get the entire thing, now you can start being like, well, maybe I want to like do some sort of bucketing optimization that like has some global impact on the entire step. But I don't remember. It's been a very long time since we had this discussion. Wan Chao?
Yeah. I'm thinking about like what like I want to understand more about what exactly does it mean by like prefetching and graph breaks, because I imagine like if the prefetching can, or if the altogether or the FSCP logic prefetching can be captured, the graph break after it can run eager, right? As long as the output of your like module parameters stay unsharded.
Like I think my specific concern, like the way we do it today is with like various stream hackery things and like running ahead, and so my concern is about whether we were planning on capturing something like that. All right, but I guess I don't want to derail onto this discussion. The general I guess question is that I feel like there are a number of things where we don't like plan on supporting graph breaks in the middle. And so I feel like that like to me that feels like the general direction we are kind of moving in inevitably as a project, where like there are a number of features that require no graph breaks in the middle, such as like control flow ops, I guess VMAP, things like that, autograd function, and so on. I saw Brian and Greg had their hands up.
Oh, I had like anecdotal example of the FSDP graph break thing you were saying. I think one is like FSDP uses data tricks to free memory. It's hard to get that to work with compile. So today we get that, the way we get that to work is we like figure out that it's a no-op between the beginning and end of the forward. And therefore, if there's a graph break in the middle of the forward, we can no longer like figure that out.
I see. Yeah.
I was going to ask for examples, which you gave. I'm not convinced that those examples are like the same as this, and that like, I don't know, control flow ops, like kind of the part of the point is to not have a graph break. That's not a very precise statement, but like, you don't really need control flow ops like in general. You need them for like computation efficiency, whereas this seems like a kind of different example. It's not a very good articulation, but hopefully the like direction makes sense.
Or I guess in this point, this is like, I mean, level 2 is entirely like a computation efficiency thing, right? It's like basically we want to provide this feature. It's not really feasible to provide this feature without capturing a graph.
I understood that argument for level 3. I didn't understand it for 2.
You're as in you don't understand why it can't be done in eager, or you don't understand why this is like a computational efficiency thing for level 2.
Not that it can't be done in eager, but why a graph break is catastrophic.
I mean, like in general, like I don't think we can even support a graph break for torch compile plus selective checkpointing. And level 2 is like yeah, even more extreme version of that. Driss?
That was kind of my question. Does this apply to level 1? At least for the
so
version?
basically, I think for level 1, we can provide an eager API for selective checkpointing. But I do not think we can do eager. I don't see a way we can do selective checkpointing plus eager plus torch compile. Or sorry, selective checkpointing plus torch compile plus no graph break, or sorry, plus graph breaks. Yeah.
I think you mentioned this like during the Monday meeting, but like I don't completely understand the argument for like why it's fundamentally impossible for no graph breaks plus selective plus compile to work.
So like my general or at least I don't like there was not a like the previous proposal for doing activation checkpointing plus with graph breaks under torch compile doesn't work for level for selective checkpointing.
Oh,
and my I guess my general feeling is that it's always possible to build something that like you can hack something to like work together, but I just feel like we're adding too much complexity to the problem. Like as in you can always like find some way to like channel information between like API 1 or like selective checkpointing plus I don't know like async collectives or something like that. But there's no way like I think this just like makes our stack more complicated over time. And like between the choices of like making our stack more complicated and just mandating no graph breaks in the region, I prefer like no graph breaks in the region.
Horace, but like isn't one problem like we're like trying to diagnose a problem with some model that's using activation checkpointing. We asked the people to turn off torch compile because that's one of the standard ablations we do, and then their stuff just doesn't like they can't run it anyway because they're ooming now.
Well, I feel like this has like always been a problem, or like this is kind of like more of a fundamental problem.
Well, but like today we mostly have the property that like you can still run your stuff without torch compile.
I mean, you can always like fall. I guess in this case, for example, you can always fall back to just full activation checkpointing, which would allow you to run your thing without dooming. Although with like different computational properties.
Okay, so I don't know. I don't feel like we got a resolution on this topic today, Horace. I don't know if the right answer is to have more one-on-ones with people, or a lot of people were just like, "What? Why is it so difficult?" So a further exploration on the implementation might be helpful because we didn't really talk about implementation in the presentation today. But yeah, I'm not exactly sure how to drive everyone to consensus. Obviously, if you implement a thing and it only works with torch compile, like I mean, it's the shipping code wins argument. So like it's very hard for us to stop you. But like if you do want to like convince everyone, I think we probably need to dig more into the implementation question.
Well, I mean, so I think I probably will ship level 2 separately. I think the main question is whether we can support selective checkpointing with no graph breaks, or like sorry, is there a way to support this API or like level 1 plus compile with graph breaks in the middle? And I guess my position is such that I don't think it's feasible enough to like seriously explore an idea. But I'll think a bit more about it.
Just and then we'll quit.
Yeah, to ship level 2, are you going to ship level 1 in eager at least?
Yeah. We're like I definitely want level 1 to work in eager. Like that's like important. Like me saying no to that would feel just more vindictive than anything else. Like I think there's a clear way to do it in eager, and it's I think obviously something people want. So I think we should do it. It just I don't think level 2 can be done as nicely in eager mode. Although, sorry, actually, one thing that is possible, perhaps, is if you run level 2, you can perhaps cache a policy that allows you to run a level 2 in eager mode, which may be an acceptable compromise for folks.
Okay, thanks everyone. See you all next week.